Okay, so starting with the page that says Bohr diagrams, I had one person this morning squeeze the Bohr diagrams into the little Lewis diagrams page. So starting with this chunk that says Bohr diagrams, we're going to review how to draw some Bohr diagrams. Now, depending on who taught you in grade 9 and 10, Bohr diagrams take on slightly different views depending on who taught you. Some teachers just put the protons in the nucleus. Maybe in grade 9 they had you put the protons and the neutrons in the nucleus using the atomic number and the mass number to figure out the neutrons. We already know how to figure out neutrons. We practiced that when we did our atomic notation, so I'm not interested in the neutrons, all right? Some teachers have you put a full circle around there and put little dots on the circle, and that's great, and that's an important way of doing it because it does show you on how the electrons are distributed, but again, you've seen that in the past. For my Bohr diagrams, very easily and very simply, and I wonder if black is actually black. Yes, it is. Excellent. So very simply and very easily, in the space for your hydrogen atom, I would like circle, number of protons, there's your nucleus, so the atomic number essentially, a semicircle with the number 1 representing the first orbit and representing that there's 1 electron in that orbit. You may have seen that before. Have you seen that method before? Yeah, variations of it. +1. That's +1 to represent the nuclear charge or to represent the number of protons. Okay? So then all the way to the other side, and I don't have a whole lot of room here, but I'll move all the way to the other side, your version of helium +2, 2, and there we have our Bohr diagram. And hopefully, from what I've explained in terms of Bohr's atom, that orbit is full. We head back to the other side, lithium +3, 2, 1. And they were supposed to be side by side. My one's kind of falling over. You get the idea. And working my way across here, beryllium in the beryllium spot, +4, 2 in the first orbit, 2 in the second orbit. 4 electrons and 4 protons. If you understand and see the trend, continue to work your way across the table. Eventually, I want you to ultimately get to calcium, all right? So you can continue with that. I'm running out of room here. I'm going to just put a squiggle here, and I'm going to jump all the way over to neon, all right? So I'm jumping all the way over to this one here, which means when I get to neon, it's going to be +10, because that's the atomic number, 2 in the first orbit, and 8 in the second orbit. Okay? And then on to sodium, +11, 2, 8, 1. So go ahead, fill in the rest of the Bohr diagrams, and then at the bottom of the page there's a handful of short questions talking about, compare the number of orbits, blah, 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 blah. And just answer those and we'll take them up in a moment. Maybe to just clarify, this was lithium, this was what, beryllium? That one was neon, and this one was sodium. It's 11. You just don't have glasses with you, or choose not to use them? Choosing not to use them. Yeah, choosing not to use them. Now again, I'm going on the assumption that you've seen this 2 times at least in the past. This is the 3rd time. If you don't understand where something comes from, by all means, it's my job to take care of that right now, but I think this is review. We're pretty well not doing anything fancy here. So just let me know if we're still not sure where these numbers are coming from. And the reason we're going to stop at calcium, we've recently learned that in the 3rd energy level, there's actually 18 electrons that can fit in it. We actually put these 2 in the 4th, but then these guys have them put back into the 3rd, and then their Bohr diagram really doesn't make a lot of sense to being able to explain how elements bond and react. So their chemistry is a little different, and even further down, even more complicated. We're just going to be dealing primarily, when talking about bonding, elements in groups 1 and 2, and then 13 to 18. We will use some of these guys in here, but I would never make you draw a diagram like a Bohr or Lewis diagram of a cobalt, because it's not a simple thing to do. You really can't do it with the theory that we have. Okay, I'm hoping we're down to answering the questions at the bottom with a little bit of something. If you're not quite there, if we could just take a look at those right now, we can work on them together. Nothing groundbreaking here as well. We're just looking for trends in terms of numbers of orbits and outer electrons, things that you've learned in the past. What do you notice about the number of energy levels for elements within the same period, right? Remember, period is a cross. So what do we notice about the number of energy levels for elements within the same period? What do you notice? Carissa, what do you got? The same number of orbits or energy levels. That is exactly correct. What happens to the number of energy levels as you go down a group? So if we move down a group, let's say we choose group 1 and you look at all your pictures and we move down a group, what happens to the number of energy levels? Yep. It increases by 1. All right? And hopefully you've noticed, what does that period number represent? So if we look at all of them in the 3rd period, what do you notice about all those elements in the third period? What does that period number represent? Yep, Lily? The number of energy levels. All right? So if I'm talking about something in the third period, right? 3 down, it has 3 energy levels or 3 orbits. Okay? Or 3 shells. They all mean the same thing. What do you notice about the number of electrons in the outermost orbit for elements in the same group? So again, if I choose group 1 and I look at the outer electrons, what do you notice about them? Yep, what do you got? They're all the same number. Excellent. And how does this compare to the group number? So if it's group number 1, and if it's group number 2, what do you notice? Yeah, so the group number tells us how many outer electrons there are. And that's very important. Again, hopefully this is very much review, but what we need you to take from this is the period number tells you how many orbits it has, and the group number tells you how many outer electrons there are. Okay? 1, 2, we're not going to worry about these because the way their electrons are in orbits are a little different, but essentially 3, 4, 5, 6, 7, and 8. We're okay with that? All right? I do want to add a little more of an explanation to this. So let's write this just on the back of this page as a little bit of an add-on note, and I'm going to just start a new page. So the first thing I want to do is I want to define a term called valence, all right? And maybe something called the valence shell, or the valence energy level. I'm going to go with valence shell. What is the valence shell also known as? Yep. It's the outer shell. It's the outermost shell of the atom. Excellent. The outermost shell or energy level. The outermost shell or energy level. Excellent. And I'm going to just put one more here as well. The valence electrons. So if I'm talking about the valence electrons, yep. Yeah, it's the number of electrons in the outer shell. Excellent. Number of electrons in the valence shell or outermost shell. All right? The term valence, you've probably heard in grade 9 and grade 10. We like to use that term. It's one of these funny words, valence. Why would somebody put something like valence in front of electrons, and why would it mean outermost? Just a little bit of a background. Again, as you know, I like to find out what words mean, so it helps me understand what it means. The term valence has the same root as the term like valor, all right? It also has the same root as the word like Valhalla, right? That's what Norse mythology. When the Vikings die, they go to Valhalla or something like that. Does anybody have no Norse mythology? No? Anyway, the root of that word, all of those words, the same root, that start of the word, represents or means power, all right? And so, if the Viking was very powerful and they died and they went to Valhalla, excellent, good stuff. And the word power in terms of valence comes from a historical study of the chemicals. When chemists were beginning to start to determine what chemical formulas were by taking a compound and breaking it apart, usually with heat or with electricity, they found that they ended up with a certain ratio of atoms that came together. So an example of this, if hydrogen was bonded to beryllium in a chemical like beryllium hydride, then you ended up with a formula that looked like that. That's supposed to be 2, not a Z. And when hydrogen bonded with something like boron, you would get something like this, BH3, and with carbon, BH4. And then with nitrogen, again, you'd get NH3. We'll talk about why that is, why it declines again. You might know. And with something like oxygen, you'd get OH2, which is also known as H2O, but that's, I just put it there so it would look like the rest. And for something like fluorine, you'd get FH, and actually you get HF. But I think you get the idea. And Chemists didn't know why they were getting formulas like this because they didn't know about atoms or they didn't know about compounds. What they knew was about ratios of masses, and they could get it from ratios of the masses of the stuff. So they described the bonding power of a chemical. Not knowing atoms, they just simply described a bonding power, that something like carbon had the bonding power to bond with 4 times hydrogen, and something like nitrogen had a bonding power to bond with 3 times hydrogen. And so this power to bond was given the name valence. It means power, right? The power to bond. We now know, because of the theories of electrons and protons and neutrons, that this bonding power comes from the outer electrons. The number of outer electrons that are available to share or to bond or to trade with, right, to make a bond, determines how that bonding takes place. So we now ascribe that term valence to the outer electrons, because we now know it's the outer electrons that gives the chemical its bonding power. Okay? So that's where the term valence comes from. It's very important that we use that term and understand it. Okay, one other important thing that goes with Bohr theory that I need you to know for the next little lessons that we're going to do on these periodic trends. In the near future, when we're done talking about our Bohr diagrams and our ions, we're going to be comparing atoms on the periodic table, and we're going to compare them for certain properties. And one property we're going to look at is the size of the atom. How big is one atom compared to the other? And really, it's going to be a fairly simple thing to do. I just need to guide your thinking in order to have you analyze it. But if I asked you to compare, say, potassium to lithium, you might be able to tell me what you think. Which do you think is larger? Without me teaching you anything, which atom do you think is bigger? Yep. Yeah, why would you say potassium? The atomic number? The atomic number tells me about the number of protons in the nucleus. I don't know about that logic. I'm not sure. Yep. It's a heavier thing? That's interesting. I guess it is heavier, but all that mass is found in the nucleus. Yeah, I don't know about that logic. What do you think determines the size of an atom? What do you think determines how big an atom is, Lily? Yeah, it has to do with where those orbits are, how far out the orbits are. That determines our outside size of an atom, all right? If you were to try to touch an atom, I don't know if you could do that. Let's imagine you could get onto a magic school bus, per se. Does that still have meaning? That's a television show of the 90s. It used to have a lot of meaning. We know Miss Frizzle? We know Miss Frizzle? Excellent. So let's imagine we could get on some kind of magic school bus, per se, and we could zoom into an atom. I guess the question is, what would you see? There's going to be a nucleus there that's phenomenally small, and then there's going to be electrons, and they're going to be zinging around all over the place in the orbit, right, in that shell. Now, what would that look like? I often imagine, if I could actually do such a thing, that it would look like something like looking at a fan that's running. You know what I'm talking about? You look at the fan that's running, and you can see behind the fan blades, but you can also see the fan blades. And I guess if you wanted to try to touch the fan, I actually have a cat story that goes with this. I'll save it for later when I'm not recording, so that the whole world doesn't hear my cat fan story. Anyway, if you could touch the fan, well, of course, your finger would get chopped off or something like that, so you couldn't do that. But you could imagine then that there's a bunch of electrons going around, and they're going around so fast that you can't really see the orbit, but you can kind of see through it. Would it be translucent? Maybe. And if you could touch it, would your finger get chopped off by an electron coming by? Who knows? Or would it be going so fast that you would actually bump into an electron and you could actually push it like a bubble? Boom, that type of thing. That's the way I sometimes think of what an atom would look like. So when we talk about the size of an atom, we're really talking about where those outer electrons are. So now we can go back and look at our logic. Which is larger, the potassium or the lithium? Yep. Less pull on the outer electrons. Why is there less pull on the outer electrons? And so gravity's going to be pulling in on the electrons? The force of gravity is phenomenally small on an electron. Gravity doesn't affect an electron. We're thinking way too hard on this. Which is bigger? Potassium. Why? Its position on the table really doesn't have anything to do with its size. It has more orbits. Thank you very much. How many orbits does it have? It has 4 orbits. How many orbits does lithium have? 2. And therefore there's more orbits, and it's going to be bigger. This is going to be a fun next week with you guys. Really fun, in a psychotic, painful way. Let me talk a little bit about the size of those orbits, because this becomes an important thing. It was not a trick question. I do want you to write this down. A little nucleus, that's a little plus in the middle of the nucleus. Oh, the glasses have made an appearance. Excellent. A little nucleus right there. And I'm going to put an electron around it. And I'm not going to call it a Bohr diagram or anything. It's just the first orbit. All right? And we call that first orbit n equals 1. That's the first orbit. Now, it turns out, and I used to do this mathematical calculation with my grade 12 university physics students, because by the end of the physics course, you have enough knowledge about the way electrostatics work and about the way electrons behave and about the way orbital mechanics works, that you can actually create an equation, the same equation that Bohr created, such that he predicted the radius of the orbits. And his equation, the radius of the nth orbit, is actually related to the square of the orbit number. All right? So what that means is the size of the orbit is actually related to not the orbit number itself, but the orbit number squared. So let's think about what that means. In this first orbit, then let's call this first distance to the nucleus R1. And it doesn't matter what it is. We could calculate it. I could find that number, especially for a hydrogen atom. It's very well known. It's a particular distance. It's not very big. It's a very tiny little distance. And now the question becomes, when I talk now about the position of the second orbit, my question is, how far out do I have to draw it? Well, I'm starting with the first orbit, and now I'm going to go to the second orbit. I'm doubling the orbit number. But the orbit's radius is related to the square of that number. How far out am I going to have to draw this compared to the size of the first orbit? Lily, what do you got? 2 times farther away. Since I doubled the first orbit, since I went from 1 to 2, it's going to be twice as far. That would be true if the radius was the same as the orbit number. Double the orbit number, double the distance. But it's not the same. It's related to the square of the orbit number. So if I double the orbit number, what's going to happen to the distance if it's related to the square of that number? Bradley? Square what? I have to square a number. I can't just square a distance number. Nope. I've doubled the orbit number. It doesn't make it double the distance. It's related to the square of the orbit number. How much further out is it going to be? 4 times. Because the orbit number is 2, and it's related to the square of the orbit number, which means the second orbit is not right there, but it's actually, that's 2, 3, 4. It's actually out here, and it is actually 4 times the distance. R2 is equal to 4 times the first one, because it's related to the square. Which means if I next want to draw my, this is n equals 2, if next I want to draw the third orbit, how many further than the first am I talking about there if it's related to the square of the orbit number? Yep. It's going to be 9 times out there, which means this is 4. So if I just kind of estimate it, there's another 4. That's 8. I got to go 1 more. It puts me out here. There's the third orbit, n equals 3. The distance out to R3 is 9 times R1. Not only do the orbits get larger when you go to higher orbit numbers, but they get larger really fast. They get really big. How many times out is my 4th energy level going to be compared to the first one? Yeah, Carissa? 16. I can't fit that on my page. If I'm looking at this, 16, this is what, 9, 16 is going to be out here somewhere, out the door. Where's the 5th one going to be? 25. That's way across the hall in Ms. Murray's room. All right? The 5th energy level is 25 times away from the nucleus than the first. So when I ask you, which is bigger, rubidium or sodium? Rubidium's a lot bigger. It's not just bigger, it's huge compared to sodium. Sodium is going to be out at a distance of about, 9 times the first orbit, and this thing's going to be like 25 times the first orbit. Way out there. Way out there. And the mathematics predicts it, and experiment proves it. It measures it. Okay? So this really doesn't have anything to do with drawing Bohr diagrams, because when you draw a Bohr diagram, you just draw the orbits, right? But I do want you in the back of your mind to realize every time we add an orbit, its distance grows by a large amount. Okay, let's now continue on and talk about the Lewis diagrams. So you can flip your page to the side. Bohr diagrams are great and all, right? Bohr is just a fun name to say. But in actual fact, it's got a lot of information we don't need. It turns out that the inner electrons don't participate in bonding. They don't have the power to bond. They're not valence electrons. So when we want to talk about chemistry, we don't care about the inner electrons. We only care about the valence electrons. Also, to write the number of protons is kind of a pain, because the number of protons tells us the number of protons, but if I put the symbol instead, right away I know what atom I'm dealing with. So the symbol is better than putting the number of protons. So Lewis diagrams, we simply put the element symbol on the inside, and we put just the valence electrons. So, for hydrogen, a dot. That dot does not have to be in the 12 o'clock position. It can be at the other positions that we'll review. But for now, we'll draw it there. It's in group 1, 1 electron in the valence shell. Away we go. Off to the other side, helium. Now, you may have learned to spread those electrons out because they repel each other. There are other rules that govern where electrons go. We will learn more detail about that in grade 12, but it turns out that when you get to the filling of an orbit, electrons will actually start to pair up. all right? Has to do with their spin, because they're actually spinning as they go around, and they make a little magnetic field, and then that little magnetic field interacts with the other one, and you don't have to worry about it. Blah, 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 blah. But they do pair up at some point. Moving back to lithium, Li, single dot, all right? Moving over to beryllium, Be, and now we don't pair them up, all right? I already sent it down, all right? So we don't pair them up. And that's because within the 8 orbit, there are actually 4 little sub-orbits. You don't know about that yet. You don't have to worry about it. But they stay separate for 4 until you get to 5, and then they start pairing up, all right? So it's like there's 4 little sub-rooms within that 2nd and 3rd orbit, okay? So, jumping across the transition metals, and I'm just going to put a break in here. I get to boron. How many dots? 3. Carbon, how many dots? 1, 2, 3, 4. I don't pair them up yet. Like I said, 4 sub-rooms, and they're separate. Okay, here we go. How do scarecrows greet each other? Hey, man. Hey, man. Made of hay? It is a good one. They're so excellent. Good. Good weather. All right, I got to keep going here, Mark. After carbon, we've got nitrogen. How many dots? 5. 1, 2, 3, 4, 5. Oxygen, how many dots? 6. If you know the way they pair up, you don't have to go around in circles, 4, and then pair them up. We're going to have 2 pairs and 2 that are alone. Fluorine, 7. 3 pairs, 1 that's alone. Doesn't matter which one is alone. And I'm out of room, neon, all paired up. Okay? Moving on to sodium and A, single dot. You should now be able to complete it all the way to calcium. And just one last thing, in order for you to do the extra ones at the bottom, even though I am dealing with maybe elements down here, we don't worry about the transition metals. So if I wanted to talk about bismuth, what would the Lewis diagram of bismuth be? What would the Lewis diagram of bismuth be? How many dots? Yep, 5 dots. It's going to look just like a sodium except with Bi in the middle. 5 dots means 1 pair and 3 lone. Okay? We can't really draw Lewis diagrams, again, simply of the transition metals, so I won't be asking you that type of thing. Groups 1 and 2, and then 13 to 18. So you can go ahead and finish that for a moment or two.